So we're going to continue on with example 7 and 8. I got a little ahead of myself in the previous video. That's just on restricting the domain of the squaring function so that we can make sense of z to the 1/2. And so in particular, since the squaring function, let me just try to draw a picture to recap that. The squaring function understands things to the right of the imaginary axis when we restrict the domain, and then on the imaginary axis, but not the negative imaginary axis. So our squaring function is going to take that, and it's going to sort of fold it out. It's going to push points out. That is, it doubles their argument. And so if this is our z-plane, if w is z squared, then our w-plane is going to look something like this. All of that green sector is going to get folded out. This line, this non-negative imaginary line, gets sent to the negative with a non-positive real axis, and then it just stretches circularly everything. And so we're going to get actually, when we square, we're going to get all of c. And then the point is that this is now 1-to-1, and it's now onto when we restrict the domain. So z to the 1/2 we want to think about as going backwards. So this is z to the 1/2. Really, I should be writing w to the 1/2. So it should be like z is w to the 1/2. But your book sort of abuses notation and puts z everywhere. So I'm going to continue to do that. So we're going to think about this. We're going to think about this as the 1/2 function, where you can pick your favorite variable to go there. Okay, so here we have the set of points where the modulus is less than or equal to 3. Okay, that's a disk of radius 3, but we don't want all of the arguments. What we want here is just the arguments that are between 90 degrees and 135 degrees. Okay, so if we were to draw that, it would look something like this. And so what we're trying to understand is what does this come from? So what's the picture over here? Let me draw an axis. That gets sent to this pizza wedge here. It's inclusive of 90 degrees, so we have a slice there. And if we think about this, what should z to the 1/2 do? Well, if we were to write our z as r e to the I theta, where theta is a principal argument, this is arg z, then z to the 1/2 is r to the 1/2 e to the I theta over 2. So what we have to do is we have to half our angle, and then take a half power of our modulus parameter. So let's do exactly that. So we'll do some algebra, then we'll scroll up and see what happens. So if z is less than or equal to 3, then this is going to tell us that the modulus of z to the 1/2 is less than or equal to 3 to the 1/2, which is the square root of 3. And if our argument is between 90 degrees and 3 pi over 4, 135 degrees, then if we half it, that will be the argument. If we half either side, that'll be the argument of z to the 1/2. So let's see, this is going to be on the left-hand side pi fourths, which is 45 degrees, which is half of 90, great. And then 3 pi eighths, which is like 45 plus 22.5 is 67.5 degrees, something like that. So our modulus goes to a maximum of root 3, and our angle varies between 45 and 67.5, if I did the math right in my head. So let's mark the original 3, And then we're going to go to root 3. Root 3 is about 1.7. So we're going to start at an angle of 45 degrees and go out about 1.7 and then go halfway to 90. So the image of that circular wedge under the square root function, the principal square root function, is this other wedge, which is much smaller. So the image of the wedge under the principal root, so whenever we write this, we mean the principal root, is the circular wedge modulus z less than or equal to the square root of 3, and pi fourths less than or equal to the argument less than or equal to 3 pi eighths. The 1/2 stuff here is just to do the arithmetic. Once we've done it, we want to then describe the set using the variable that we're using in the plane. All right, so that's it. And so it's very similar to what we've been doing, but since we're using a half power, we have to use the principal argument, and that's where the extra difficulty arises.